Okay, let's now take a look at the principles of protein-protein binding, which is also the same as kinetics, is the same as protein-ligand binding. So let's focus on protein binding. Now to start off with, we're going to be looking at the interaction of two proteins. We'll call this protein A and protein B. These two proteins in a solution, when added together, protein A plus protein B, will generate a complex between the two proteins, forming what is considered a heterodimer. Hetero means that the two individual proteins are different from each other. Dimer means that it is a bimolecular interaction. Now recall kinetics. This is going to have an on rate, which is abbreviated small k on in the forward direction. The on means the association of A and B to form B. This will happen at a specific rate. Because this is a non-covalent interaction, we can also have the AB dimer dissociate, come apart, and to form the individual monomers of protein A and protein B. And this has a measurable rate also, which is considered K off. Now for other nomenclature, in the forward direction we have two independent different molecules that are going to interact to form one molecule. Because we have two molecules interacting, the forward reaction is considered a second order reaction. The reverse reaction is having a single molecular entity dissociating into its two components. So the reverse reaction, because there's only one molecular entity involved, this is called a first order reaction. Now the objective of measuring protein binding kinetics, which again also applies if this was a protein and a small ligand it binds to, kinetics are the same, is to measure the binding affinity. Binding affinity gives us a lot of information about protein-protein interactions and protein-ligand interactions by telling us how tightly these two entities interact. So to determine the binding affinity, what we have to first consider is what's called the association constant. The association constant is defined as K sub A, and this is the concentration of the products over the concentration of the reactants. So this is going to be the concentration of the single molecular entity AB complex that is formed in this reaction over the individual concentrations of the reactants A and B. This will also be reflected in the rate constants. The rate constant of formation of the complex, which is K on, over the dissociation of the complex, which is K off. Now the units of the association constant units are going to equal the inverse molar. And this is because we have a concentration, molarity here, and two molarity concentrations here. The numerator and denominator in one case will cancel and will be left over 1 over the molar concentration, which is m minus 1. Now this is a very unusual unit number, and so we typically don't try to deal with this very often. What is a better unit to deal with is straight molarity, the inverse of this. So the way we can determine this is to define a factor called Kd, which is the dissociation constant. As you can imagine, the dissociation constant is going to be the reciprocal of the association constant. So Kd is going to equal 1 over the association constant Ka. And we define Kd as the inverse of Ka. So this is going to be the concentration of A, concentration of B, over the concentration of the single molecular entity that is the product. Likewise, the rate constants can be expressed in the form of Kd, and this is going to be, of course, the reciprocation of the association constant, so K off over K on. The units of this, of course, is the reciprocation, so it's going to be straight molarity. This is a much easier figure to understand and interpret and communicate, so most of our discussions about protein binding kinetics, whether it be protein-protein or protein-ligand, will be concerned with measuring the Kd. So now the next question is how to measure Kd. How do we measure the dissociation constant? Well, first of all, we have to consider that we have a second order reaction where we have two reactants coming together to form one product. So this means that A and B are independent variables. So in order to do this measurement properly, we have to have only one variable in the reaction. So we need to hold one reactant, either A or B, constant when we do our experiment. So in our example, let's propose to hold the concentration of protein A constant and in our experiment we are going to measure the concentration of the formation of A-B complex with increasing concentrations of reactant protein B. Also could be a ligand. So in this experiment, we take a constant concentration of A in all of our test tubes, and we're going to add varying concentrations of concentration of B into the test tubes, allow them to react, and then measure at equilibrium the concentration of AB formed. So the concentration, the amount of AB formed, will be on our y-axis. The variable concentration of one of the independent variables, protein B, will be on the x-axis. What would we get for this reaction if we actually do the experiment and measure? We will get a hyperbolic curve. What this means is that while holding A constant, as we increase the amount of B, we can saturate the reaction to get maximal, essentially 100% AB. This will have happened, of course, when our A is used up. Now, how do we interpret this data to get our dissociation constant? Well, let's go back to our calculation, our equation of Kd, which is equal to concentration of A times the concentration of B over the product AB. And let's look at this from this standpoint. Now, if we look at the 50% point here, which is 50% formation of A and B, of AB. At this point, this 50% point, what this means is that of all of the A we have in solution, 50% of it is associated with the AB product. 50% of it the other 50% of A is free A. So now if we rearrange our equation here for dissociation constant, just a simple algebraic rearrangement, we are going to solve for B. Because at the 50% point, we know what AB and A are. So let's say KD equals the concentration of AB over the concentration of A, and this equals the concentration of B. Now, at our 50% point, 50% of A is tied up as the bound form in the complex of AB. 50% of A is free. This is equivalent to a one-to-one relationship of AB to A. So if we substitute in these values in our dissociation constant rearrangement equation, we see that this is KD times 1. So therefore, KD equals the concentration of B. So by definition, at 50% point, where we have half of the AB complex determined, formed, if we drop a line down here to this concentration of B that permits this association, we have the dissociation constant.